As we discussed in class, the process of image registration is widely used in all types of brain imaging applications. Image registration attempts to align two images to one another such that the anatomical locations of these two images match. This is essential for being able to compare individuals to one another or being able to compare images across a larger group of data. Image registration is an important step in many neuroimaging processing workflows and pipelines and is used across different modalities such as fMRI and diffusion imaging and is a key element in the analysis of structural brain data. Before registration, we typically see a scenario like so. Image A corresponds to an individual subject that we acquired on our MRI scanner. Their head orientation is not exactly ideal, and if we were to try to look at a corresponding voxel in image A and try to align and match that to our template space in image B, we would see that those areas of the brain are not lined up, they do not match. The process of image registration tries to align these under the two anatomical locations of these two images so that when we do look at one voxel in one brain, it corresponds to the same voxel across all the different brains registered in the same space. So what do we mean by registration and what's some underlying terminology? Typically, we have three different types of images when referring to a registration algorithm. We have our input, or the image that we're trying to register, We'll have a template, which serves as a reference or template space for which to register our input image to. And then we have our output image, which is our image that has been registered to the template. To register our input image to our template, we have to apply a transformation to the image. The transformation represents the mathematical construct that takes one image and aligns it with another. The process of registration is finding the optimal transformation that aligns these two images. And then in order to align our input image to our template image, we have to apply a resampling of the image, of our input image, such that the transformation can be applied to our input and create a new modified image. There are many different types of transformations as we've discussed in class, and they can be broadly classified into two categories. Linear transformations, which consist of rigid body transformations, which correspond to having 6 degrees of freedom and includes rotations. Affine transformations, which are 12 degrees of freedom in 3 dimensions and include rotations, translations, scalings, skews, and shears. And then there are a class of nonlinear transformations, which have more than 12 degrees of freedom and can have can be highly dimensional. They're used for good quality between subject registrations, and typically you need to first perform an affine registration as a starting point. These nonlinear registration algorithms are also iterative and require a level optimization, and therefore can take a long time to perform, but generally provide a much better registration than linear based methods. So how does registration work? So typically what happens is we take our input image and try to apply some type of initial transformation that tries to align that image to our reference image. And then a measure of goodness of that alignment is computed to tell the algorithm whether or not that transformation is good. The algorithm then tries to minimize that goodness of alignment measure to find the best transformation that takes our input image and aligns it to our template. The measure of goodness of alignment is determined by what's known as a cost function. As you've probably guessed it by now, FSL has some very useful tools for performing image registration. There are tools for both linear and nonlinear registrations, but we'll only work with linear registrations due to time limitations. FLIRT, or FLIRT, Fimbrid Linear Registration Tool, is FSL's linear image registration method. And FNIRT, Fimbrid Nonlinear Registration Tool, is FSL's nonlinear image registration method. We will work with FLIRT with this lab, but check out the documentation on FNIRT at the FSL wiki page. If you type FLIRT into the terminal window, you will notice that there are many different options available when using this command. Take a look at the different cost functions that are available. These are listed under the -cost flag. In particular, FLIRT has a variety of different cost functions implemented, each that have different advantages and disadvantages. Namely, different applications may require different cost functions depending on the types of images that you're trying to register. For example, the least squares cost function generally is a good choice for when trying to align two images of the same modality, and typically using the exact same parameters. For example, two T1 weighted images acquired between two different individuals. A normalized correlation cost function is generally beneficial for, again, using when acquired using the same modality, but different brightness and contrast may slightly change within an image. The correlation ratio is useful for registration between any MR modalities, even different modalities such as between a T1 and a T2 weighted image. Mutual information and normalized mutual information, again, are great for any MR modalities, but also good for including other modalities outside of MR, such as CT or PET. And BBR is a cost function that's a within subject EPI to structure. It's specific for using when trying to align echoplanar imaging data to a structural imaging data, for example, when trying to align functional imaging data to your structural T1 weighted image. As previously mentioned, FLIRT can be used either with the terminal or command line, but it can also be used with a graphics user interface. To use with a GUI, you could type FSL into the terminal, and you'll notice from the window that pops open, there is a FLIRT linear registration button. There, if you were to select that button, a new window should pop open and will allow you to select the various inputs and outputs and reference image for running the FLIRT command, as seen here. However, we will use FLIRT from the terminal, and the general use of using FLIRT from the terminal is here. The general command for using FLIRT from the terminal is here. First, you provide an input image, which is a path to that input image. You provide a path to the template based on the option ref, and then also a path to your output image based on using the out flag. For example, if you were to register the skull stripped image that you've created using the BET command previously, you could use a command similar to the following. Or if you again CD into the test subject 1 directory, you could use relative paths as seen here. Use FLIRT to register the skull stripped brain image to our template image using a similar command as the previous slide showed. Take screenshots of the co-registered image for your lab report. After running FLIRT, what is printed out to the terminal? record the output of FLIRT using a screenshot and include this in your lab report. Standard spaces and templates are available through different neuroimaging packages, and there are many different standard spaces and templates that can be used. Two of the most standard templates or standard spaces are the MNI and Telerak. These are convenient templates that can be used for co-registration of data as well as identification of known brain regions.